Hello. Today we'll talk about vehicle stability and performance. Vehicle stability and performance. The primary goal is to create a low drag shape in a vehicle. And that's great, and that would give us a lot of aerodynamic benefit, but we can enhance the benefits we get by the creation of conditions that improve vehicle performance. The primary purpose in performance is not so much drag reduction, but there are benefits of drag reduction that come along with it. And in this section, we'll look at vehicle stability and performance. The first phase in vehicle performance is called the traction limited phase. And it's in that phase that the aerodynamic downforce improves vehicle performance with the drag coefficient remaining essentially the same. As the phases go on in the three phases, in the second phase, the drag performance becomes, the drag coefficient becomes higher with greater aerodynamic downforce. So we get the benefits of aerodynamic downforce, but we now have a higher drag coefficient. And in the third phase, you don't get any additional benefit from increasing the downforce. It just stays flat. But this is the primary section. The first phase is a very critical phase. Traction. What is traction? Well, the performance of a vehicle depends a lot on its tractive ability, the ability for it to grip, the tire to grip to the ground and to be able to effect motion. You know, Newton's third law, action and reaction. The tire hits the road, pushes forward, and is able to effect traction. So performance of a vehicle is rated on its tractive ability, that is, of the tires, and on the drag forces experienced by the vehicle. Coefficient of road adhesion, that's how well the tire grips the road. We want adhesion, not cohesion. Cohesion will be between the material of the tire and itself and the material of the road and itself. What that does is makes the tire slip on the road because the tire is holding to itself. We want adhesion, the grip between the tire and the road. The normal load on the drive axle that pull the weight forward, the load acting on them, and how well they move the vehicle moves the load along, the power plant and the transmission. These are the things to look at in vehicle traction. In this study, we'll look at traction. As we've said, we'll look at power requirements, tire contribution to vehicle stability and performance, underbody flow. Underbody flow, as you'll see eventually, especially when we look at severe service vehicles, underbody flow will become a very important aspect to consider in the design. And we'll look at the truck-car passing interaction. Whenever we're on the highway, there's always the overtaking, the car overtaking the truck. There are some aerodynamic interactions that take place during that process. We'll look at that and try to give it a broader and a more detailed view. This is your typical vehicle in a slant, a little bit of a slant, theta sub s, which is small. The forces on this car, they include the aerodynamic resistance R sub A, which is right there, as the aerodynamic resistance. The rolling resistance of the front and rear tires. So R sub F and R sub R. This is R sub F, the rolling resistance, because the tire is going this way. The tire is going this way. So That's the rolling. So this is the rolling resistance in the front. The same thing by the same motion. That's the rolling resistance in the back. So we have our R sub A and R sub F. Um, uh, the grade resistance R sub G, which is defined as W, which is the weight of the vehicle, written there as the weight acting down at the center of gravity, but it's W sine theta sub S. We've already defined theta sub S right here. So W sine theta sub S is along this direction, and that is the grade resistance. So if the grade is small, the grade resistance will be small. If the grade is large, the grade resistance will be large. So this is the grade resistance going this direction, W sine theta sub S for a car of weight W. The drawbar load, which is right here, whatever material is being pulled, and the tractive forces in the tires, F sub F, which is here, the tractive force, that's that which grips to the ground and moves forward, and F sub R in the front and rear wheels. So those are essentially the forces in play. Some other little forces that may be present can be grouped into these categories. And this is the distance between the front and the rear wheel. That's our distance L. And from the center of gravity to the rear wheel we'll define as L2. That's L2. And from the center of gravity to the front wheel we'll call L1. Those are the parameters that we're using in establishing our equation of motion. This dynamic equation we have for this arrangement and is m mass times the acceleration, m d squared x dt squared, is the sum of all these terms that we have expressed. Now we do some elegant solution. We group these terms together and we'll arrive at general expression for W sub F. That's the normal load on the front axle, W sub F. That's right here. This is W sub F. The normal load on the front axle is expressed in terms of the load on the vehicle. And this is the load on the vehicle at rest. This component represents the load at rest, and this portion is the dynamic load. This is for front wheel drive. For the rear axle, we have a similar expression where this is the portion for the static loading, and this is for the dynamic loading. So we go on and clean this up, develop it further, do a few mathematical manipulations, and we come up with a final expression for the maximum tractive force. That's where we're heading, the tractive force. The maximum tractive force for the front wheel is defined as that, and that for the rear wheel is defined as that. So we find the forces that are responsible for traction, the forces that will be in play for the parameters that have been given. We've just looked at the tractive force determination for a car. For a tractor trailer, it's a little more complicated because we have to look at two aspects. We have to look at the tractor itself as one entity and the trailer as another entity. And in treating that, this pretty well describes it. So we are treating two separate entities that form a handshake in the final analysis. So this is the tractor portion is treated, and this is the trailer portion is treated. When we do this, these are just, from the basic laws of mechanics. When we apply, say, a certain force to the tractor in this direction, the corresponding force when we're treating the trailer component has to be in this direction, and that's what's indicated here. Whatever is applied to the tractor, whatever is applied to the tractor, the trailer has the opposite sense of that force. We see that here, and we see the same thing here. So we keep that in mind. Other than that, the treatments are essentially the same. Just keep tab of the sign, that the positive or negative sign. And following the same expression as we had done for the car, we would come up with the reaction at the trailer rear axle. That's what's of interest because tractors are rear-wheel drive. So we'll just pay attention to the rear axle and the reaction at the rear axle when we look at all these forces that are at play with an approximation that considers the theta very small. With theta very small, sine theta is essentially is equal to theta. So this will not hold if theta is very, very high. And it's not often that would come across very high grade anyway, so that approximation makes sense in terms of what happens in real life. The reaction at the trailer rear axle is now obtained in this form. Why is that important? It's critical to the proper sizing of the tire at the rear axle. Once we know that reaction, we can properly size the tire that should go to that location. So the goal is to determine W sub n, and from there go on and do our proper trailer rear tire sizing for the trailer rear axle. Let's look at power requirements, where, of course, assuming equilibrium of forces at steady speed. That's a simplified form to be able to look at power requirement. This is the trend of power requirement, the expression for power that is supplied for an efficiency, that efficiency. So this is the total active power supplied with the efficiency taken into account, eta times P. The expression for the power supplied is that, and it's equal to an expression of the third power of the speed, and just a single power of the speed for mechanical power required. This is mechanical, and this portion is aerodynamic. So the power required to supply the mechanical to overcome the mechanical obstacle and to overcome the aerodynamic obstacle. It turns out that at low speed, the mechanical power required is actually dominant, as we see here in the very low speed, below 50 miles per hour. The mechanical power required, it's at the initial phase dominant, and at some portion just about the same as the aerodynamic. But as the speed increases, we see the significance of the aerodynamic power required. It shoots out because the aerodynamic power required varies with the third power of the speed, and the mechanical power required essentially levels off more or less in a straight line, because it's only the force the tractive force times the speed. So this goes on to show the significance of aerodynamic contribution, especially at highway speeds. As the speed increases beyond the critical value is the point of intersection between the mechanical power required and the aerodynamic power required. At the critical value, beyond that, you have the aerodynamic power required becoming dominant. Now, for various engine power settings, 25%, 50%, 75%, as the engine power setting increases, the power required becomes very high. This will be the maximum power required at this point for the total power. You can see this is the total power, the sum of the mechanical and aerodynamic power required. And for a given engine setting, typically a 75% engine setting, you have this as the total power, 100% power. But as we can see, the sheer dominance of the aerodynamic power required as the speed of the vehicle increases. So aerodynamic force becomes the dominant force at high speed, shall we say, at highway speed, whereas the mechanical force, the mechanical power required to overcome the mechanical devices is the dominant one at very low speeds. You know, the stop-and-go street speeds, there's no significance of aerodynamics there, but when you get on the highway, it becomes the dominant parameter. Okay, contribution of the tire. The tire is responsible, the presence of the tire is responsible for drag coefficient increase for up to 0.08. And that's significant. And for lift coefficient increase of up to 0.3, between 0.3 and 0.58, and that's really major. The tire itself does not cause increase in lift coefficient, but it generates the condition that causes the increase in lift coefficient. What do we mean? Well, let's look at the lift increase quickly. This essentially is our tire, going, forward. The wind, this is the front of the vehicle. So the vehicle is going that way, and all this flow coming here hits this. We have our stagnation point here. As the air hits this, and the tire rolls, it shoots out entrained air movement with a lot of force, a lot of pressure that go to hit the bottom of the vehicle. And when they hit the bottom of the vehicle, they generate lift. That's one of the major ways where the presence, where tire is responsible for the increase in lift coefficient. To reduce that, we have to look at a critical design of the tire so that there's little lift that is generated. Also, as the tire rolls along, gets to this point, it becomes, it generates lift from this end. At this point, the speed is twice the speed of the vehicle, because right here we have the initial speed v, but as it rolls along, the speed increases, and here the speed is 2v. And also, with that speed, there's an amount of pressure as it hits this material. It becomes a pressure that goes up there to create lift on the vehicle. So you have lift being created on the vehicle due to the tire here and here also. So you can therefore see where how you can have such a high increase in lift coefficient due to the tire. This is dynamic that takes place in the tire position. the pressure here is greater than the ambient pressure in this location. We have the stagnation pressure, and the tire takes, the pressure on the tire takes that form. We have high pressure there, and then it's bulging out here. And here is where it bulges out more. So the P here is less than the ambient pressure. And what the pressure is here is such that it lifts it up. It's in the upward direction. And that's not desirable. We want downforce on the car. If you remember from earlier on, we want the car to grip the ground. We don't want lift. We want inverse of lift. We want downforce. Downforce, that's what's required for improved performance. But what happens here is a reduction in the downforce. But that is essentially the dynamics of the tire in a vehicle, doesn't matter which. The effect is more significant in cars than in trucks, and we'll see in a moment when we look at trucks, but that's essentially what happens. Now, looking at this, let us look at some of the things that we can do. Well, we can have two extremes. We can have a tire radius. We can have a tire that's very thin, just more or less like a thin line, to a tire that's so wide it becomes like a cylinder. Well, you want the tire to be wide because the wider it is, the more it grips on the road, and you want that traction. You want the adhesive force between the tire and the road to be significant. The wider the tire is, the greater will be the adhesive force between the tire and the road for a given tread design, of course. And studies have shown that the drag coefficient on the wheel, due to the wheel, reduces as you go from here. This is value H. H is the height of this opening for the tire. The housing is the height of the housing to the underside of the car, and R is the radius of the tire. So what we have then is the larger the radius of the tire, and the smaller the housing, that we will have various effects. The combination is such that the drag coefficient depends on the ratio of this H to the radius of the tire. H over 2R, the larger H over 2R is to a critical value. The larger H over 2R is, which means increasing the height of this opening, of this, okay? When you increase it up to a point, you have drag reduction. After a while, if you increase it beyond that, it really doesn't create improved performance. It actually causes an increase in drag coefficient. And the reason that that happens is as you have this increase, after a while you have, beyond the critical point, you have this becoming sources of drag that increase the drag on the vehicle. And so the larger this becomes beyond the critical value, the greater the body that's exposed to drag, and greater is the drag on the vehicle. So H over 2R, for a given vehicle, there's no fixed value for H over 2R. It depends on the vehicle you have and the dimensions. Aerodynamic testing has to be done. Real vehicle testing has to be done for each car design to determine the critical H over 2R. And beyond that value, the drag coefficient due to the wheel will increase. Now, what do we have between the width of the tire and the diameter of the tire? This is twice the radius. This is again 2R. D equals 2R. So B over 2R, we say B over D, which is the same thing as B over 2R. B over 2R has to be less than 1 for effective performance. That's a reduction in the drag coefficient for the car. And when B over D or B over 2R becomes higher than 1, as the further it is away from 1, the greater the tire becomes more like a cylinder. Yes, it grips the road more, but it becomes a great obstacle and a drag, actually, and it becomes ineffective, and the performance of the car it becomes poor. So these are the critical values. You want your B over D, which is B over 2R, to be less than 1. Maximum to be 1. Usually B over D equals about 0.7 is what the race car users, the race car users and some drag car racers use in a number of ways. Everyday car usage, for typical family car, you have B over D to be, for typical family car, you have B over D to be about 0.4, and that's typical utility for vehicles. Okay. There are some tires that are being designed these days that are really very thin, and the thinner it is, the less the stability of the vehicle, because the less it grips to the road. It's important to have a tire that's wide, fairly wide, to about 0.4 the diameter of the wheel. What kind of resistance do we have due to tire? Well, it's a graph of the aerodynamic drag over the total drag, where total drag is the sum of the aerodynamic and the rolling drag. As we see, certainly below 70 miles an hour, some critical value, the rolling drag is influential because of this is the total drag coefficient that we have for each drag coefficient. This is the variation of the drag with the speed. Now, as the speed increases, we see that the rolling drag becomes irrelevant, because at about this point, maybe a little beyond 70 miles per hour, we have what's more or less a flat line, and that's D over D, which is 1. It just essentially, we have the drag coefficient again being essentially determined by aerodynamics. So this, at high speed, therefore, we can approximately say the drag present in the vehicle. We can literally ignore the rolling drag and just approximate the rolling drag and the aerodynamic drag as just the aerodynamic drag at high speed. Okay. So what all these are showing is the significance of aerodynamics at high speed. It's a high-speed phenomenon. Well, got to be careful about what we define as high speed. When you start to have a speed beyond 50 miles an hour, in almost all cases, the aerodynamics becomes very significant. Underbody flow. What's the contribution of the underbody flow to vehicle performance? Well, to increase the downforce, which is the desirable thing, the car should be as close to the ground as possible. We can't make this the case for trucks, but for cars, it should be as close to the ground as possible. So the cars that are low to the ground are more stable because they have greater downforce. Let's look at 2 instances. This is a car that the leading edge, look at this design. Right from the onset, these are 2 designs interposed one on the other. Let's call this 1 and call this design 2. So if we look at design 1, the height of 1 from the ground is this. Well, as the wind comes, the air comes straight on, this is what happens. The boundary layer is generated, the flow, the air flows, and it goes that way, and it hits the ground at some point there, which is like halfway along the entire length of the vehicle. Whereas if the vehicle is lower to the ground and made aerodynamic, okay, you have your boundary layer built this way, and it comes again. It's more smooth rather than hit the ground here, which will cause lift. It's more smooth and it merges with the ground there, and this is the height in this case from the ground. So this reaches up to here. This lower one reaches up to here, which means more or less it's almost passing the length of the car before it hits the ground, and so the effect of it here does not hit the underbody of the vehicle, and it is therefore a better design. So it is important to lower, whenever possible, you want to increase the downforce. You should have the car as close to the ground as possible for increased downforce on the vehicle. I want to talk finally about truck-car passing interface. A couple of different schools of thought have been presented in a car-truck passing interface. But what I have done is actually gone to the highway and done this experiment. I must have done at least 40 runs over a span of about 5 years. So this is a documented thing in real life. I've done this on the highway. I've done this in most of the highways in the country and in different road conditions. So this is not merely a wind tunnel simulation. This is a real life thing that was done. Please don't do this without proper training. But this is what has been observed to happen, what we will describe now. We'll look at 3 phases. The car approaching the truck, that's one phase. The truck and the car in the truck environment, that's another phase, and the car pulling away from the truck influence. This is based on a straight head-on wind. We're not talking about wind at various angles now. Let's look at a very simplified case. In the book, Introduction to Theory and Applications of Aerodynamics for Ground Vehicles, in another chapter, the details of the wind coming from different directions are treated. I just want to look at a simplified case here. So we have again those 3 phases. 1, the car approaching the truck. 2, the car in the truck environment, and 3, the car pulling away from the truck. So what happens? As the car is approaching the truck, the wind, this is direction of motion of both the car and the truck. As the car is approaching the truck, there's boundary layer on the side of the truck. There's flow deflection. The flow goes that way, and it creates a wall. These are high speed, and for the car to pass the truck, the car is going at a speed higher than the truck. So we're talking about maybe one car going at 75 miles an hour and the car going at about 65 or 70 miles an hour, so that the car eventually overtakes the truck. But what happens is there's flow going this way. There's a flow hitting the car, and as the car comes this way, this flow is hitting the car this way. So this already creates a wall on the car because the flow coming down is powerful and it just pushes through. So essentially, the car is experiencing an air wall around here, and this flow coming here then hits the car. So what it tends to do is it hits the car and keeps going this way. So what it tends to do is steer the car in this direction. Well, the driver wants to go straight, so sometimes subconsciously, the driver may not even be aware. The driver is actually steering to this direction to keep a straight path. That's what happens before the car gets into the environment of the truck. That's just closing out to the back of the truck. That's one case. That's that case, the car approaching the truck or the car just behind the truck. Now here, the car is in the environment of the truck already. Well, things are a bit more comfortable in a way, apart from when it's raining and the spray and the soil hits the car from the tires of the truck, apart from that case. But in general, the flow keeps going this way, parallel to the truck. Again, there's flow deflection, flow scattering from the wheels of the truck, depending on how well the truck is covered. That we don't see that much of that when there's side skirts on the truck. But this is not one that's considering that. Generally, the flow goes that way, and so the car is in this environment with a truck beside it, and the flow is going that way. Occasionally, there's turbulence because of this flow that's going here, and there's a little flutter on the car, but generally the car can go on steadily beside the truck for quite a while. But that is not the idea of overtaking. That's not the purpose of overtaking. The purpose of overtaking is to shoot out from the truck and keep going. So with that in mind, what happens is that the car, in an attempt to shoot out, gets here, and it wants to move out of the truck environment. Now, this truck has a blunt surface area, as you can see from here. So it's already had the air before it compressed. So it's that compressed air that covers this whole area, including the region of the car. So that compressed air comes like that, and as it comes, it shoots through with high speed. And as it shoots through, it creates a vacuum because this is high speed, high velocity, and when there's high velocity here and there's no velocity here or relatively lower velocity here, the pressure here becomes higher than the pressure here. So we'll call the pressure here P2, and we'll call the pressure here P1. P2 is higher than P1. So what happens? Pressure pushes to the line, to the place of least pressure. And let's describe that here when we look at here. When we look at this diagram, compressed air is shooting forward. You will have this force coming across, but again, it's not a straight force. It's a force that's coming, as we've shown it here. It's a force that's coming in like that, okay, into the vehicle here. So it has its component which hits the vehicle straight. It has its other component which pulls the vehicle to that direction. What's the bottom line? The bottom line is that the car is pulled towards the truck, and the driver actually has to literally steer his car away from the truck to be able to go straight. And this has been observed many times. Over several years, this has been done. This has been tested. So Again, what do we have? As the car is approaching the truck, the car is essentially pushed away from the truck, and the driver has to do this so they can go straight. In the region of the truck, this is a side area influence of the truck. Things are a little more stable for the car beside the truck. And as the car passes the truck, the tendency of the dynamics of air in this region is to pull the car towards the truck, and the driver needs to make the effort to steer the car away from the truck to keep a straight way going. Why are these important? Well, it's important to know this because it makes the driver aware of the danger in hand, and the understanding of this will certainly increase highway safety and awareness, both for the driver of the truck and especially of the car, who is in a greater danger than the one on the truck. But it's important that both sides know this. And these are the phenomena that are taking place in a car-truck interaction. Again, this is based on the assumption of a straight flow. There's no curve on the highway, straight, and the wind is head-on or still wind. The dynamics become a bit more complicated when you have various road conditions, when you have curves and bends and a number of all of the things. But in this simplified form, that's exactly what happens. All right. Well, this is an elementary treatment of vehicle stability and performance, and hopefully with this you will be able to look at more advanced aspects of vehicle performance, improving vehicle performance, and increasing vehicle stability.